I forgot to turn on the mic, so probably didn't record for today. So hopefully most of you are here, but try it next time. So what happens is the amplifier in general looks like an input and an output. So that's the equivalent circuit of the triangle that we saw earlier. You remember the triangle, you have two input and an output, right? So the input side has this one, Ri, it's called input resistance. See, well, your input connects to the input terminals, right? And the output is connected to, of course, the output VO. But within that, what do you see? Is A times VO VI. That's exactly what we did in the example. And often the amplifier has an output resistance, RO, in series. So in this case, you have input resistance, output resistance, and amplifier. And this is called, do you guys remember what the voltage, that symbol, what's the name of that symbol? Dependent source, right? Great. So that's also called a controlled voltage source. So what we talk in this one, we call a voltage amplifier. Why is it called a voltage amplifier? Because that output is a voltage. And also the controlled voltage source or dependent voltage source is depending on an input voltage. So everything is voltage. So this is called a controlled voltage source or voltage amplifier. So this is a more complete circuit where you have input coming here, you have input coming and connect to the input, and you have output connect to the load, right? So now you can analyze this circuit because, so this RS is usually called the source resistance. So it's a resistance of a source. So in the future, if you get any voltage source, you get a sensor, you get a pressure sensor, or whatever, you say, oh, I got a voltage I need to amplify. So that source coming in has an internal resistance. That's called a source resistance or internal resistance. Now, these two are in series. So we also call them a voltage divider. So what are you amplifying? Are you amplifying Vs or are you amplifying Vi by looking at the circuit? Well, you see here, actually, this voltage gain is multiplied by Vi. So we're actually only amplifying this signal, not this signal. Okay, you say, okay, fine, what's the difference? Well, the difference is quite big depending on what your internal resistance. Okay, so let's say your resistance is 1 ohm, and this is 1 kilo ohm. What happens to your amplification? So pretty much everything here is here, right? Because that 1 ohm is this 1,000, so this is only 0.1% of the input. So primarily it's all here, so we can neglect it. But if we flip around, say this internal impedance is 1 kilo ohm, but this one input resistance of this amplifier is 1 ohm, what happens? The amplifier isn't really working because you got voltage coming in, 999 is here, only like 1 is here. You're not really amplifying. So you're amplifying a very small portion of your source. That's no good. So that's why in the future, if you look at any sources, you say quality. Well, the smaller the internal resistance, the better the source. For this input resistance, do you want it to be bigger or small by now? Bigger, yeah. The bigger the better. Because the bigger, regardless of this one, like, okay, let's say this is 1K. Instead of 1 ohm, you have this 1 meg. What happens? Okay, 1K, 1 ohm, 1,000 times. We don't care about this one anymore. Now, of course, you can't go really take well, in the extreme case, we have an open circuit. So what is resistance of an open circuit? Infinity, right? So in the extreme case, we have an open circuit. So whatever applied here is applied here, regardless how big is 1 ohm, 1K, or 1 meg. It doesn't matter because it's open circuit. Okay, so that's the input side. So I'm just talking, not going to write too much because that thing is not writing well. So, but this is all in the book, right? So you guys can write notes if you want. Now, on the output side, we already know that this is output resistance. This is a load device. And whatever amplified this voltage is amplified this A, and this A can be, small, big, and it can be 2, 3, 4, 5. It can be 5,000 or even 50,000, depending on the type of amplifier that you design or you select. So now let's look at the output. Why it's important? Let's say your load resistance is 10 kilo, like it's very typical in our examples in the future. And if you have internal impedance, like output impedance, like not internal impedance, well, we can call it internal impedance. This is called output resistance, RO, output. So if this is 10K, and your output resistance, let's say, is 10 ohm, what happens now? This drops very little voltage. Most of the voltage over here is applied here. It's good. Now, if this is still 10K, but this, for some reason, this has an output resistance of, say, 10 mega ohm. What happens now? Because about whatever, let's say this is 5 volts, you got like 4.9999 is here, only 0.0001 is here, right? So that's not going to work. So that gives you a conclusion is that the smaller, the better for output resistance. Now, of course, we're talking about voltage. We're talking about voltage source, right? If this is a current source, that's a different story, right? So let me draw just a few things. So say RO, RS, small is better. RI, big, is better. And RO is small. So those are the conclusions that we already made, right? So, and in the future, when we design amplify, we sometimes ask you to calculate the input and output impedance. We call it impedance in the future most of the time. We don't call it resistance anymore because impedance means it's going to be possibly inductor and then possibly capacitor, things like that, not just pure resistance. And but if it is a current source, it's going to be different because if you have a current source, and from the previous example, you already know that oops. I know what happened. Okay. So this is the amplifier. This is A times I S. Okay. So if it's a current source, of course we want this RO to be small or big. Well, see, the thing is that these two are in parallel, right? So the current in the load is proportional to the resistance of this one. See, the current divider, right? So we want this to be big because if this is bigger, and most of the current will come this way. So in this case, we don't want this small. So we want RO to be, what I'm writing here is big is better, right? So yeah, it's always opposite. Yeah, you're right. But since now we talk about this voltage source and current source, so think about, so your input can be a voltage or current, right? Right. And then your output can be either a voltage or current. So therefore, we can have 4 different combinations. So this is one combination, voltage, voltage. And the draw I draw here is current, current. But in fact, in real life, you can also have voltage, current, current, voltage. So there are 4 different amplifiers. Okay. But the analyze method eventually is going to be the same. And also in chapter, not this class, but the next class, you will be learning multi-stage. Because sometimes the amplify, one stage is not big enough. One stage, let's say maybe amplify for 10, which is not good enough. And we want more. Like in an op amp, for example, next chapter we're going to talk about, We want to reach 5,000, 10,000. How can you reach 5,000, 10,000? Well, one stage is not enough. So you need multi-stage, like 100 times 100. If you have two stage, you got 10,000, right? That's good. So that's one reason you need a multi-stage. Another reason is that sometimes one amplifier, the input resistance is not too big enough. We want big, but it's not big enough. What? So we design a circuit to increase the input resistance. And sometimes the output resistance is not small enough. It's too big. So we design another output stage, right? We have a smaller output resistance. So that's how we do it. And also sometimes we want to amplify signal. We want to have a differential amplifier, not a common ground. So those amplifiers cannot do it. So we need a differential amplifier. So this is why we need a multi-stage. So over here you can see this is a great example, because if you look at stage one, it has 100 kilo ohm internal resistance of the source resistance, but you have 1 mega ohm of that input resistance of stage one, which is great because the input resistance of this one is bigger. So most of the voltage Vs will be applied here. So then this amplifier has a 10 times amplification. So you got 10 times Vi with this one, and you got 1K, and this 100K, again, 10 times difference, right? So you amplify another one, and this is 100 times this one, and with 3, and then the last stage only amplify 1. Again, you might say, why just amplify 1? Well, because we want to make sure the output resistance is small, 10 ohms. Do you see that? But this one has a output resistance 1K, right? So 1K is too big. So we add another stage, not to amplify the voltage, but to amplify, to reduce the output resistance. But so if you want to solve this problem, I mean, it's already marked here. So basically, you can say, yeah. So yeah, there's not much to mark. Maybe I can write down I equal to Vs over 100K plus 1 meg, right? So, okay. So that's how you, and also we can write I2, we can write I2 equal to 10 V I1 divided by 1K plus 100K, right? So, and so on. Now we can write VL equal to VI3 divided by 10 ohm plus 100 ohm times. So this is a voltage divider, right? So this just like step by step, you should be able to. There's one homework on this, so you should be able to do it. Okay, this is what I mentioned earlier. So we have 4 types of amplifiers, right? So we have voltage amplifier, which is input voltage, output voltage. And then we have current amplifier, we have input current, output is current. See, the difference between voltage source and current source is the voltage source has plus minus sign. Current source has arrow. Okay. And then we have input is voltage, output is current. So we call this transconductance. And then we have input is current, and then output is voltage. We call this trans resistance amplifier. So 4 types of amplifier. Be careful in the future about the direction, because if this plus minus voltage is typically easier for students to understand. It's positive here, negative here. But for current, you know, if it's up, which means the current going this way. So if it's down, it's just current going that way. So how do you distinguish between like a positive current? Let me just show you an example. So if I want this case, I mark IX, and I want to say, so in this example, I say A IS times II. I just give it a value, say 10 milliamps. How much is IX, do you think? Yeah, just this is for this example here. AIS times II equal 10 milliamps. How much is IX as I marked? It's going to be 10 milliamps, right? It's the same direction. But I'm going to do another example here. I'm going to mark IX this way. So if this GM times VI equal to, I'm going to get different number, 5 milliamps. How much is IX? Let's call it IX2. How much IX2 do you think is going to be? Is it going to be 5 milliamps? Yeah, it's going to be negative 5 milliamps because the direction is different. So this is only one thing I just want to bring up, because students say, oh, I mark it this way. Why, like he was correct, I'm not, why he got points, I don't get points, because it depends on how you mark it. If you don't mark the direction, you simply say IX is 5. I don't know, But if I mark it already IX this way, you still say IX is 5 milliamps, you're wrong because the direction is wrong, right? So that's how you want to do that. Okay, and I will talk about output input resistance. So one of the important things is, how do I find output resistance? Like for a circuit, some circuit is easy, just by looking back you can find it. But when you have a controlled source or you have dependent source, you cannot find out by just inspecting the circuit. What would you do? You apply voltage at that output, and you look at how much current flowing into that circuit. Once you find the current, yeah, divide them, you'll get output resistance. So for example, if we get a circuit like this, okay, if for this circuit, like, can you tell me how much is the output resistance? What you're doing is just by looking back, see how much resistance. Well, it's 2 in parallel, so that gives you 5 kilo ohm. But if you have a circuit like this, and this is like GM times something like VI. A lot of times at the beginning, what students look at it saying, oh, RO is 10K. Well, you're wrong. You may be wrong, maybe right. But you cannot say it's 10K without knowing what this is about. Okay, so what you're going to do is you apply voltage. You're going to apply voltage. Okay, you call it Vx, and you find Ix. So your RO equal to Vx over Ix. Now, of course, once you apply, you will be able to find what the GM is or VI is and so on. You have to do that. But let's say you have the same circuit, but then you have and this is GM, and you have an input like short circuit. So in this case, can you say can you find your output resistance without just doing anything else? Okay, so this is GM times VI, and this is like a, okay, can you see? So this is GM times VI, yes, it's controlled. No, actually, I did it wrong, so we cannot do that. Well, we can still do it. Let's do this as a current source. So this is a current source, okay? So this is a current source. So this current source saying is GM times VI, but VI is short circuited. So when VI is short circuited, how much current do you have here? 0, yeah, GM times VI, 0. So what happens for zero current source? For a zero current source, what does it mean? Anybody else? It's open, yeah, it's open, because zero is open for current. Now for voltage, of course, it's short, right? Like yeah, voltage short, right? But open. So if this is open, how much resistance you have? Looking into, right? You have 10K. So because that is open, so this is open. When you look into it, it's only 10K. So it's how you get the Yeah. So you can use the same approach to find input resistance as well. Like for any circuit, like if you want to find the input resistance, you can look into it. If there's no like control source, you can always find the resistance. But if there's a control source, you have to apply a voltage, find the current, and use voltage divided by current. Sometimes even if there's no control source, you can still not find it because the circuit is too complex. Okay, like different connections, you can still not do it. So you have to apply it. Okay. So now let's look at a real device circuit. So this device circuit is equivalent circuit of a BJT, which is same thing for MOSFET, similar. So this is a BJT, bipolar junction transistor, So this transistor, for small signal, what does it do? Well, it takes the input, and it will have some voltage drop at its input resistance. So this R pi is the input resistance, and it amplifies that voltage into a controlled current source through a transconductance GM. And then that current also connect to output resistance. Well, this actually is not output resistance. Oh, yeah, it is, because RO in parallel with the current source. So this output resistance, and then it gives you output at the output terminal. So very simple circuit. So for this circuit, if we want to use it, it's also very simple. Connect your source to the input terminal, then connect your load to the output terminal. Now you have a complete circuit. As we did something similar before, we can analyze this circuit very easily. So let's do it together. So you guys, this is a really good review for our circuit. Okay, so what is the VBE in this case? In terms of Vs. What is the VBE in terms of Vs? Yeah? Yes. How different is it? From what? Amplifier, yeah? Oh, it is amplifier. BJT is amplifier. Well, later on you'll get to that. Yeah. Now, BJT is a device. It's an amplifier. In particular, in this class and 430, of course, when you get to say 584, it's no longer an amplifier. It's actually a switching device. Yeah. But yeah, amplifier, a name for MOSFET and for BJT. They're, like for now, they're amplifiers. Okay. Yeah. So okay, so let's look at the input side. So if you look at the input side, okay, even though I said use nodal analysis, but actually here you have to do a loop analysis, but it's not that difficult to do a loop analysis. What is VBE? Can we do it together? Or what is the relation between R pi and RS? What kind of connection? It's a series connection, right? Okay, so, and then if they're in series connection, it's a voltage divider, which means we can divide the voltage of input between R pi So this is how you get VBE. This is a voltage divider. Now, of course, let's review the concepts. R pi is the input resistance of the amplifier. RS is the internal impedance of the source or source impedance. Okay. You can also, again, switch that word impedance to resistance. That's okay for now. Okay, so that's what we do. Now we found VBE. If you're given GM, you will know the current. So the next step is let's find the current of here. IO. How much is IO in relation to GM times VBE? And sometimes we can call this IB. Okay. So let's write down IB. So IB is equal to GM times VBE, right? So you see the direction that I marked IB is that direction. So they're the same direction. If I mark VBE that direction, you will get negative, right? Okay, so how much is IO? Can we do it together? What is the relation between RO and RL? Okay. But what's the connection type between RO and RL? It's a parallel connection. So if it's a parallel connection, it's going to be a voltage current divider, right? If it's a current divider, we can write the current as the other resistance, the branch of the other resistance, the resistance of other branch plus its own resistance times GM VBE, or times VB, whatever, because IB, right? So that's the same thing here. Okay, so I want to ask you, is this expression correct? Let's have a vote. How many think this expression now is right? One. How many people think this equation is wrong? Raise your hand. One, two. Why is it wrong?
They're going different directions.
They're going to different directions, right? Even though that IO, the number is correct, but the direction is wrong. So which means we have to take a negative IB going to this direction. So eventually, it's really, we have to add a negative sign over here, okay? So it's a negative, right? Yeah. So this is what I'm saying. When some student asked me the other day, is this an easy class? I said, yeah, it's an easy class. Because if you know how to do voltage divider, current divider, right? You know the relation between voltage, current, and power, and so on. So fairly easy. So throughout the book, we do this many times, especially going to chapter 7. We like to do this every day. Okay, this way, that way, this, all kind of things, we do it. So basically, all you're doing is to find out with the given input, what is the output, and your combination of between parallel and series connections. Of course, we have to find ways to calculate the input impedance, output impedance, and we have to get how we got the equivalent circuit, and there's some semiconductor physics behind it, so we have to go through all that process to get to this point. But at the end of the day, what do you use it for as an amplifier? Yeah? Oh. You want me to go back? Do you think that there will be any current going to ground? Not in this circuit. There's no current going into the ground. Right. So like you have loops. You have loops already. So this part is purely here for reference only. Okay. Oh, and then we're saying, okay, well, that sounds really simple. But then sometimes we have to make the problem even a little bit more difficult. Now, it's not the purpose to make your life more difficult, it's actually we need it. Because sometimes we found, well, for some circuits, yeah, it's that simple. But for some circuits, we find using the same method, we cannot get an answer or cannot get an answer easily. So what do? Well, we change. So this is how we change. Instead of having the BJT like initially you had, we have another like a resistance connected over here. Now, once you connect resistance over here, you have trouble because now, you see, this is one of the problems, especially in the beginning of this class. Students say, oh, let's say input is 10 volts. And I'll give you right away, I'll give you an example. And I'll ask you guys what's wrong with it. So a student says, okay, R pi is 5K, and RE is also 5K. And we have Vx equal to 5 millivolts. So then one student was saying, oh, I get this mic here. On the circuit, we have V pi. So he said V pi will be equal to that 5K divided by 5K plus 5K times 5 millivolts equal to 2.5 millivolts. Is it right?
No.
No, why not? They're in series, yeah?
All that would be if it was only receiving current from VX, but it's also receiving current from VI.
The problem is that RE is not in series R pi. There's another branch coming in, right?
Well, it's not purely that series.
It's not in series, right? So then what do we do? Well, in this case, we have to do some either loop analysis or node analysis to find out the voltage of the current. Now, if we want to write, so as example, I want to write the nodal analysis on this one. So let's call this voltage. When you do nodal analysis, you need to define a voltage. So let's call this VE. So how many nodes do we have in this circuit?
4, maybe 5, if you want to get.
Yeah, but how many independent nodes?
4.
No. Just one. Okay, I'll let you guys figure out why is one. So gonna see. Okay, I'm gonna have to cross it out because otherwise she doesn't take it. So around VE, we do nodal. So VE, we can say 2 current coming in and 1 current coming out. So the current coming in is Vs minus VE over R pi. That's the current coming in from R pi. Plus the current coming in is beta times IB equals current coming out is VE over RE. Well, once you get to this point, do you see 2 current coming in? The current coming this way, which is this Vx minus VE divided by this one. And this current already given, but it's controlled, right? And then this current coming out, which is VE divided by RE. That's the voltage between these 2 terminals, okay? So if you know some of the parameters, you will be able to derive right away what you need to find out. This one actually is not called Vx, it's actually called Vs. Let me correct. Vx. I need to learn how to erase next time. Okay, so that's what you have. And also in the future, in this class in particular, we always refer an amplifier as a linear amplifier. So a linear amplifier means what our input is amplified to output with a linear ratio, 3, 4, 5 times, right? So that's a ratio. So we can have a couple examples to see what's the difference between a linear amplifier and a nonlinear amplifier. So let's say this is the input, and this is so from here to here, you're only amplifying the magnitude, the frequency doesn't change. So this is called a linear amplifier. But what happens, let's say you have another signal, this, but your output what happens to this one? Well, it sounds like a linear because it did amplify, but somehow it didn't amplify the middle part because it's too big. It got what we call sometimes we call saturation. It's no longer linear. So it's a nonlinear amplifier. But for linear amplifier, you always amplify the input. The output is the same waveform. But we do add this little phase inside. That's called a phase shift, which means you can have, say, let's say this is your input, but your output could be like this. So the difference between we are. So the difference between input and output, there's an angle that's called phase shift. Phase shift. Yeah. And okay, so that's between linear and nonlinear amplifier. But what happens is when you have amplifier, let's draw amplifier here. And you have an input. There you go. So for the same amplifier, let's say one day you do this. You do this input. I'm just going to ignore the angle, just saying that this is the same phase. Okay, you guys say the ratio between VO over VI equal to 10. So okay, this is example 1. Okay, so the next day you do this. You do, but then you find that your gain is this much. So this is V in, this is VO. And your VO, okay, VO over V in equal to 0.5. Okay, so I was post here, so ask you guys what's going on. So for that, I got 10 times the amplification, but for this one, I only got like 0.5. Output is not actually big, actually small. What happened? What's the difference between these two waveforms? Other than the magnitude change different. The longer period, but the bottom one has a frequency, a lower frequency, longer period. So, okay, so I'll give you, again, one more example. So you're going to say, okay, so, and then one day I'm going to use this one with like, okay, and then you find the output. Okay, so this doesn't really draw. So then let's say just VO divided by V in equal to 0.1, and it's actually become maybe nonlinear, but anyway. So, and again, similarly, what happened to this one? Because the frequency is too high. So, but you might say, oh, that's a same amplifier. What happened? Why is it like sometimes big, sometimes small? Well, this comes to a frequency response. For the same amplifier, if you change the frequency of input, the output doesn't always respond the same way. Typically, in the middle band, we call it from certain frequency to certain frequency, the middle band, they're good, like constant amplification. But below that frequency, it's not going to be that good. So we call it, so sometimes we need to understand what's going on in this area. So we call it low frequency response. And sometimes we want to look at what's going on here, this high frequency response. So how the amplifier respond to a high frequency, how the amplifier respond to a low frequency. The middle band is always good. Now, the good thing for you guys that in this class, you only have to worry about the middle band. Okay, so whatever we give you, we assume it's in the middle band. Now, the middle band, of course, can be different for different devices. Like some device may be from 1K to 100K is the middle band. But for another device, it could be from 100K to 1 meg is the middle band. Or maybe for another device, it could be from like 1G to 5G gigahertz is the middle band. So it depends on the device, right? So the middle band can be very different. It doesn't mean the same range. So that's that. Now, of course, if you do the frequency response, you will know that this RC, the CR circuit. Let me ask you guys, if you guys forgot already, on the top, if the frequency is very low, what happens? If the frequency, like, okay, let's say it's a DC, what happens?
It will be let through, but it's either they will be let through or won't be let through, but it will be
So if the frequency, like in DC, for example, current won't flow through C at all. So eventually the battery gets charged, I mean, the capacitor gets charged to the whole voltage, right? So if the frequency goes higher, very high, and you know that impedance of C is what? 1 over omega C, right? Your omega is very high, 1 over omega C becomes 0. And all of a sudden, like you have the maximum current, which is V over R. Okay, so yeah, so the top is sometimes called high pass, right? The high frequency gets to go, I mean, low pass, for example. Right? And then here is a high pass because when the C is very high and this becomes like a 0, yeah, and then all the voltage apply here. But the first one, when the frequency is very high, all current going through, but the voltage is 0. So high pass, low pass is what we define. So all transistors behave similarly in this case, right? So, and then did you guys learn body plot somewhere? This term, body plot? Yeah? Or maybe body up type wrong, should be BODE. I'll change that. Yeah, so that tells you like how the response of a circuit, you know, respond to a different frequency. So like in this case, this range is called low frequency or middle band, but it's like a low pass. For high frequency, the output is smaller and smaller. So it's like a low pass, like cut off. And this is the angle. Okay, so like phase shift, maybe 0 phase shift, and all the way 45 degree and a 90-degree phase shift. So that's a body plot. We'll do this a little bit in, I think in chapter 7 we'll review this one, but and this is for low frequency response or high pass. Yeah, you know, high pass means for high frequency, the amplification is the maximum, but as frequency drops, the gain becomes smaller, and the same thing in the bottom is phase shift, right? So that concludes our chapter 1. So this is so much. Now you guys can go on to homework number 1 and try to submit on time. And then next week, we're going to dive into chapter 2. It's more fun, actually. And also next Thursday, my grader, my TA is going to come here to do the demo on how to use PSpice, LT Spice. Okay. See you next week, guys. Mhm.